Hey, welcome to the graphing review. All of these problems come from your last review that you had for your last test. So you can grab that out or look at, find it on the student files if you would like to actually work these along with me. So when we graph a function, we want to make sure we know what the parent graph is. And in this case, the parent graph is absolute value. And that looks like this. And we want to find the locator point. That's actually really important so we can see where to put it. And then we're going to, last but not least, do the dilation, which is kind of new. So that's what we're focusing on. So we know it's a absolute value, and the locator point is the HK right here. This is the locator point. So in this case, the locator point is 3, 1. And that is because the negative is already there, so we're just going to drop in the 3 and 1, and we're going to plot that locator point right here. And this is the 3, 1 locator point. And we know it's going to be absolute value. It's just going to look something like this. But the 1/2 means it's been compressed. So it's kind of a little fatty fraction. So we know it's going to compress along the y, and it's going to be it's going to be compressed down. So that's what we're going to try to do. But we need to do it with actual points mathematically. So the first thing we're going to do is put our parent graph numbers in. So -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. Because absolute value, the regular absolute value function, y equals absolute value of x, this is our parent, it just takes every negative number and makes it a positive number. So that's graph looks like this. Every 1, 1, over 2, up 2, over 3, up 3, -1, up 1, -2, all from the locator point, -3, up 3. And here is the graph. And if you notice, I didn't make a new table, I just used the parent graph table, and I counted all of those from the locator point. So over 1, up 1, over 2, up 2, over 3, up 3, and that saves you a lot of time. So what you're doing is you're taking this parent function and you're actually compressing it by half. This is a compression along the y-axis, so that means you are taking 1/2 of y, basically. So now, instead of it going -2, 2, all the y's have been halved. So it's 2 divided by 2, which is 1, 1/2, 0, 1/2, and 1. That means every y value, instead of doing what we did before, which was over 1, up 1, we are now going to only go up 1/2. So I'll show you what that looks like. So instead of going over 1, up 1, you're going to go over 1, up 1/2, which is here. Instead of going over 2, up 2, you're going to go over 2, up 1. And if you think about it, if you had 4 before, now you have 4, 2. So you go over 1, 2, 3, 4, and up 2. Same direction, over 1, 2, 3, 4, up 2. So as you can see, this drastically, when you connect those points, compresses this function. Okay, let's try this one. Hit pause and try it yourself, and then come back. All right, so we have a parabola here, x squared, a nice quadratic. So that parent graph is a little bit different. That parent function is going to be -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and if I went further, 3, 9, it's just squaring everything. And so our locator point comes from here. So our locator point is actually -1, 1, because it's x minus h. So -1, 1 is our locator point right there. And normally our function goes over 1, up 1, over -1, up 1. This is the parent function we're squaring from the new 0, 0. Over 2, up 4, 1, 2, 3, 4. Over -2, up 1, 2, 3, 4, etc. So these are our points for our regular function if we're not dilated. However, we are. In fact, this dilation is going to be a 2 It's a number larger than 1, so it's going to be a stretch. Stretch it up. So 2y. So that means every y we had before, now we're going to do it times 2. So 4 times 2 is 8. 2, 0, 2, 8. Woo! And then 18. Really large. So I'm actually going to erase this guy because he's going to be in our way. We're going to keep our locator point right here. This is our negative 1, 1 is our new 0, 0. And from our new locator point, we would have gone over 1, up 1 right here on either side. But now it's doubled, so it's over 1, up 2. Over negative 1, up 2. And then over 2, instead of going 2 and 2 squared is 4, it's 2 and 2 squared is 4, but then you have to times by 2, which gives you 8. So from here you go over 2 and up 1, 2, 3, 4, 5, 6, 7, 8. Woo! And then over 2, 1, 2, 3, 4, 5, 6, 7, 8. Very, very, very skinny. That gives you a lot of great points really quickly. Let's try another one. Oh, our fun square root function. Hit pause and try it. Okay, now we're back with our beautiful square root function, which looks like this. Don't forget. Oh, actually, that kind of looks like a square root, doesn't it? Very fun. Okay, and our locator point here is 2, 1. So over 2, up 1. That's our new 0, 0. And remember, our square root function, if you have y equals the square root of x, you're not going to be able to do negative numbers. So like negative 1, negative 2, they're not going to exist in our parent function. So we're going to start with 0, 0, and then we're going to do 1 squared is 1. And we're going to pick numbers we can square, like 4, because the square root of 4 is 2. And the square root of 9 is 3. We're going to make that nice and easy. And then we're going to talk about how we dilate this function next. So if we were just doing the parent function from here, it'd be 0, 0 over 1, up 1, over 4, 1, 2, 3, 4, up 2, and over 9, 1, 2, 3, 4, 5, 6, 7, 8, up off the page, 9, up 1, 2, 3. So that would be our beautiful parent function right there with added dilation. But now we get to add dilation. And that dilation is 3. So that means we're going to stretch it up again. So all of our y values are now going to be multiplied by 3. So that means for our parent graph, 3 times 0 is still 0, 3 times 1 is 3, 2 times 3 is 6, and 3 times 3 is 9. So instead of going, so this is our other function. I'm going to leave it here, but instead of going, we're staying 0, 0, so the parent graph stays the same. Looks like he got moved over just a hair. There we go. So the parent graph stays the same. And then we are going to graph the dilation. So 0, 0 doesn't go anywhere. Then instead of going over 1, up 1 like we did before, we go over 1, up 3. So over 1, up 1, 2, 3. See how that stretches it? Woo! And then over 4, 1, 2, 3, 4. So that kind of I'm going to clean this up a little bit here. Okay, so you can see me counting. Over 1, 2, 3, 4, and up 6 instead of 2. So 1, 2, 3, 4, 5, 6, way up here. And then 9, 9. So we're off the page, but instead of going up 3, we go up 9. So we're going over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up here. That gives us 4 beautiful points, a really nice dilated graph, and you're all done. So now if you have a graph and you have to write the equation for it, then you just need to write what you know. So let's look at this one, for instance. Right here we know this is absolute value, so it's y equals a x minus h plus k, and we know our locator point is going to be negative 8, 0. So we're going to plug that in. So we plug that in, we plug in a negative 8, and then instead of the k right here, we're going to plug in plus 0. And then we can rewrite that much more nicely, like y equals a, x plus 8, absolute value, and we don't need to put the plus 0. Now we just need to solve for x, or for a, I mean. So to do that, you need to pick any other point on the line. What we're going to do is we're going to put in a point for x and y. So because now we have 1, 2, 3 variables, but we can't solve an equation if we have 3 variables. So we know we can put in an x and a y from anywhere on this graph, and then we can plug it in. So let's pick a point. Any point. This is a nice point right here because it's on the axis. So this little point is actually 0, and then 1, 2, 3, 4. 0, 4. That's a nice point because we love when we have 0. So x is going to be 0. We're going to plug in 0 for x and 4 for y, and then we're going to solve for a. The absolute value of 8 is 8. 4 equals a times 8. We're trying to get a by itself, so we're going to divide both sides by 8, and that gives you that a equals 1/2. Once you know that, you can write the equation. Y equals 1/2 x minus 8. Or plus 8, sorry. All right, try B part. All right, let's do the next one. This is a square root graph. Woo. So this is going to become a square root here. And our locator point is, oh, look at that. Again, -8, 0. So when we write that, we're going to replace the -8 and 0 with h and k. So x minus -8 plus 0. Again, when we simplify that, y equals a square root x plus 8, and we don't need the 0. This is going to be so now we need any other point on the line. You can pick any point you want to plug in because, again, we have too many variables. We have 1, 2, 3 variables, so we can get rid of this variable and this variable by picking a point off the graph, any point you want. But I like to pick easy points. So let's pick a nice easy point. Let's see. How about you could pick this point here. You could pick, I pick lattice points, they're the easiest. Ooh, or this point here, that one's really nice. Because that point is going to be 0, 2. So that means x is going to be 0, y is going to be 2. So we're going to go in here and plug in 0 for x and 2 for y, and then we're going to solve this equation for a. Alright, so we have 2 equals a times the square root of 8, and I don't know if you remember, but we'll go over here and make sure we remember how to do the square root of 8. That's 4 times the square root of 4 times 2. You can take the square root of 4, that is 2, but you can't take the square root of 2 evenly, so we're just going to leave it 2 root 2. So 2 equals a times 2 root 2. We need to get a by itself, so we're going to divide both sides by 2 root 2, which makes this lovely. So that gives us a final answer of a equals 1 over root 2, and we can write that as, if we rationalize that, a equals root 2 over 2. So you can write the final answer as y equals root 2 over 2, or you can use a decimal, times the square root of x plus 8.